Fantasia that I did for Monday's lecture, which is all about the vasculature. And that hopefully will get us caught up to where we're supposed to be. Any questions before we start? Yes? Yeah, I'll do 2 quizzes to kind of catch us up on things. I'm like a quiz behind on where I want to be because of Monday. So I'll put up 2 quizzes sometime this afternoon. I'll make them available for Thursday, Friday, Saturday, and Sunday, and you can take them at your leisure. They'll be, I won't put them on lockdown, and I won't put a password on them, so that's all you'll have to do is go in, log in, click on it, and take it. But there will be a time limit. So I figure if it's 10 questions, 12 minutes should be enough to answer 10 questions. Other questions? If I have to run to the water fountain or stick a Halls in my mouth when my voice starts giving out, please forgive me. Somebody stole my water bottle, either one of my kids or my wife, and the only bottles in the refrigerator are beer and soy sauce. I didn't think either one of those would be appropriate. So there's 2 things in the cardiovascular system that we have to deal with. We have to deal with the heart, because that's the pump, that's the driving force behind what goes on in the cardiovascular system. Then we have to deal with the blood vessels, the vasculature. So we're going to talk today about how we can regulate blood pressure. So normal mechanisms for regulating blood pressure, keeping blood pressure within normal limits. Normal blood pressure is between usually 120/80, right? Your systolic number over your diastolic number, which gives you a mean arterial blood pressure of about 90 to 93. So that's what we're going to deal with, are ways in which we can regulate blood pressure. So there is autoregulation. So individual organs and tissues can auto-regulate blood flow, and that's based upon demand, metabolic demands. So if you're using more oxygen, if you're a highly metabolically active tissue, you're going to be making more CO2, right? And you're also going to be making more acidic byproducts, so there's going to be more hydrogen ions, there'll be a lower pH. So those things go into auto-regulation, so regulating blood flow to a tissue based upon its needs, its metabolic activity. And then there are other ways to maintain normal blood flow. Neural mechanisms, as we know, are fast, they're rapid, right? The response is rapid. You have a stimulus to a receptor to an afferent pathway, and you have integrating centers or control centers in the brain for regulating blood pressure, which are going to regulate heart rate and constriction and dilation of vessels. Those are the ways to alter blood pressure. And then there's going to be an efferent pathway that goes out to both the heart and the blood vessels. And that's going to be a rapid mechanism for maintaining normal blood pressure. So if blood pressure falls, there's a rapid mechanism in response to that that's going to bring blood pressure back up so that you don't pass out. Blood pressure is too high, there's a rapid mechanism to lower it so you don't burst a blood vessel. Endocrine mechanisms, as we know from the endocrine system, take longer than neural mechanisms, right? It takes a while to manufacture and secrete those hormones, particularly if they're steroids. The effects, they have to travel through the cardiovascular system, they have to bind to the receptors and affect the tissue, so that's going to take a while. So these endocrine mechanisms are more long-term, right? They're going to take longer than the neural mechanisms, and they're going to give you longer-term effects. We remember from the autonomic nervous system, blood vessels are innervated by the sympathetic nervous system, not the parasympathetic system. The only blood vessels innervated by the parasympathetic system are yes. Genitalia? Yes. That's it. All other blood vessels innervated by the sympathetic system. Now, you could have some that are innervated by the sympathetic cholinergic system. That's about 10% of the sympathetic nervous system activity, but most of them, you're dealing with norepinephrine and epinephrine binding to either alpha-1 or beta-2 receptors. Alpha-1s cause constriction, beta-2s cause dilation. So these are all going to be sympathetic nerve fibers. There's going to be fibers going to the arteries and to the veins. 2/3 of your blood in normal resting circumstances is in the venous circulation. If you need to increase blood flow, one of the best ways to do it is to constrict the veins and force some of that blood into the arterial circuit. Small arteries and arterioles, you can control blood flow to an organ by sympathetic nervous system release of norepinephrine, stimulating alpha receptors. So if you want to increase blood flow, you would release less epinephrine. You'd get less alpha receptor stimulation. If you wanted to decrease blood flow, you would release more epinephrine, and you would get constriction because of stimulation of alpha receptors. Ways to increase arterial pressure. Mean arterial blood pressure, usually called MABP or sometimes MAP, mean arterial pressure, either one, depending upon the book you read, is proportional to, you can't calculate it from these values, but it's proportional to the cardiac output. So how much blood is coming out of the heart in any particular time, and systemic vascular resistance. What's the state of the vasculature? A lot of contracted vessels gives you a higher resistance. A lot of dilated vessels gives you a lower resistance. This systemic vascular resistance is sometimes referred to as peripheral resistance, so you may see it as SVR for systemic vascular resistance, or TPR for total peripheral resistance. It's the same thing. So constricting the arterioles increases your total peripheral resistance, your systemic vascular resistance. Constricting large vessels, increasing venous return. So venoconstriction can cause an increase in blood return to the heart. And increases in cardiac output, whether it be an increase in stroke volume by contractility or heart rate by stimulation of the SA node. Those are all going to be ways that you can increase blood pressure. Nervous control, if you're in an exercise or fight or flight situation, there's an area in the medulla called the vasomotor center, the VMC. What it does is it controls the state of the vasculature. Do you have vessels that are constricted? Do you have vessels that are dilated? And that alters resistance to flow. That alters your peripheral resistance. Increased sympathetic activity, decreased parasympathetic activity is going to increase SVR. Now remember, the sympathetic system is going to increase heart rate, contractility, and constrict blood vessels. That's all the parasympathetic system does, is control the heart, right? It'll lower the heart rate. So it doesn't have any effect on the vasculature. So the effects of sympathetic stimulation: increased resistance, increased venous return, increased heart strength, contractile strength and rate, is going to give you an increase in arterial pressure. So those three factors I just talked about again, listed here. Constricting arterioles, increasing vascular resistance, constricting large vessels to get more blood into the heart, right? Increasing venous return, and then directly increasing cardiac output by stimulation of the SA node and by increasing contractility, so the beta-1 receptor response to norepinephrine and epinephrine. So as far as the baroreceptor reflex is concerned, so the nervous system controlling kind of minute-to-minute alterations in blood pressure. You have these baroreceptors. Baro means pressure, like barometer. So these are mechanoreceptors in the arteries, the large arteries, that then feed information to the vasomotor center, which then is going to feed information to the cardiovascular control center for the heart and the vasomotor center for controlling the vessels in order to alter cardiac output or total peripheral resistance. So the baroreceptor reflex is good for short-term regulation. And these are pressure receptors. So they're basically sensitive to the amount of stretch on the arterial walls. Right? So these are receptors that are embedded in the arterial walls, and as the amount of blood or the pressure inside the circulatory system increases, the stretch, the force on the arterial wall is going to increase as well. So a rise in pressure stretches these baroreceptors. That's going to increase the rate of firing action potentials to the brainstem, which the brainstem, because it understands frequency coding, right? That's how the nervous system communicates, is by frequency coding. Then senses that increased action potential frequency as high blood pressure. Blood pressure is too high. Or if there's a decrease in action potential frequency, it senses that as low blood pressure, and then initiates the appropriate response. So these baroreceptors are found in the internal carotid arteries. Blood in the internal carotid arteries goes where? Albuquerque? No? Where is blood in the internal carotid arteries going to be going to? Brain. So it's very important to monitor the pressure of the blood going to the brain, because you don't want to burst a blood vessel in the brain. That's called a stroke, a hemorrhagic stroke, and that would be bad. And you don't want blood pressure to the brain being too low, because deprived of oxygen for a mere 5 seconds, you will pass out. So it's very important to monitor that. And then the aortic arch receptors basically sense the pressure as it's coming out of the heart going to the systemic circulation. Information from these carotid receptors are going to be traveling through the glossopharyngeal nerve, cranial nerve 9, up to the vasomotor center, and then information from the aortic arch receptors traveling through the vagus nerve, cranial nerve 10. Typical frequency coding system. So as you can see here, as pressure goes lower, normal mean arterial pressure is somewhere around 90-ish. Let's say 100 for the sake of argument. So if this is considered to be normal, then this lower action potential frequency is going to stimulate a response to increase heart rate and constrict blood vessels to increase pressure. And then this higher action potential frequency is going to stimulate the parasympathetic system and give you decreased blood pressure, arterial vasodilation. All right, so typical negative feedback mechanism. During your normal cardiac cycle, you get a period of systole where pressure is going to be high, right? The heart is pumping blood into the arteries, so that's going to stretch those arteries and cause stimulation of those baroreceptors. And then diastole, during relaxation, blood is moving forward in the circuit, pressure decreases. Right, so you can see the action potentials show up here strongest during the period of systole, and then weaker or go away during the period of diastole. And that's normal. That's how the baroreceptors expect to be stimulated. So any aberration, any deviation from that is considered abnormal. So how the system works. You've got receptors sending you information via cranial nerve 9 and cranial nerve 10. And then here you have what's called the nucleus tractus solitarius, NTS. Then this area called the nucleus ambiguus. Then this area called the dorsal motor nucleus of the vagus. Essentially, these two areas together, the ambiguous and the dorsal motor nucleus, are referred to as the cardioinhibitory area. So when I ask you on a test, I'm probably going to use the term cardioinhibitory area. This is not a neuroscience class, so knowing the individual nuclei is not all that important. You should know that there's going to be this cardioinhibitory area, and there's going to be the vasomotor area. So you're controlling the two factors that go into mean arterial pressure, right? Heart function, vessel function. Output from the cardioinhibitory area is to the heart. So if you inhibit or turn off the cardioinhibitory area, it's no longer inhibiting the heart rate will increase. If you stimulate the cardioinhibitory area, heart rate will decrease. This is one of the hardest concepts in physiology for students to grasp. The idea of having normal inhibition and then disinhibiting or removing the inhibition, right? Because it's kind of like a double negative. Right? If you're normally inhibited, you remove that inhibition, then there's an increase in activity. If you stimulate the inhibitory area, there's going to be more inhibition, and there's going to be a decrease in heart rate. And so we've got fibers that come down, stimulating the parasympathetic system in the heart. So release of acetylcholine stimulating M2 receptors in the heart, causing a decrease in heart rate. That's your normal cardioinhibitory function. Right? I said that normally the SA node fires action potentials around 90 to 100 times per minute. It is this normal cardioinhibitory or vagal tone which keeps your heart rate down around 70. So inhibiting that inhibition causes heart rate to go up. Then there's also direct stimulation via the sympathetic nervous system. Right, so sympathetic outflow from the thoracic spinal cord to the sympathetic ganglion, postganglionic fibers going to the heart, releasing norepinephrine, stimulating beta-1 receptors, increasing heart rate, increasing contractility. That'll increase your blood pressure. Then, of course, there are postganglionic sympathetic neurons that are going to go to the venous circulation, squeeze the veins, cause them to contract, force more blood into the arterial circuit, increases blood pressure, and stimulation of the adrenal medulla to release adrenaline, epinephrine, and norepinephrine. And so you've got this vasomotor pathway to control the vasculature, which also influences the heart. And you've got the cardioinhibitory area, which is your parasympathetic outflow. Questions on that? Again, you've got two areas to deal with. So you can control the heart via altering the cardioinhibitory area. You can control the vasculature by altering action potential frequency coming from the vasomotor center. Ooh, polysorbate 40. Exciting. Yes? Oh, I thought I heard it over here. Echo. No, that's sympathetic. Postganglionic sympathetic. Yeah, parasympathetic system doesn't influence venous return or arterial, or unless you're talking about erections. We haven't gotten there yet. We'll do that towards the end. Oh, going backwards. So arterial pressure normally maintained pretty well between about 60 to 180 millimeters of mercury. Blood pressure drops below 60, goes over 180. Then you're at this point of the curve where it's flat. The receptors are no longer responding if it's too high. And if it's too low, again, receptors are no longer responding. They respond mostly to the change. Again, if you remember what we looked at, where you've got more action potentials during systole than diastole, what it's really responding to is the change over time in the action potential frequency. So it's not responding to, it doesn't respond more during systole and less during diastole. It responds to the rate of change of arterial pressure or of baroreceptor stimulation over time. It is most sensitive, luckily, at around 100 millimeters of mercury, which happens to be pretty close to normal mean arterial blood pressure. So if you are laying down and you decide to stand up pretty quickly, the initial effect is going to be gravity. You've got these big honkin' is a physiological term. You've got these big honkin' vessels that run from your abdomen through your chest called the vena cava, right? Big guys, lots of blood in them. You stand up, gravity starts pushing blood down away from the heart. So you're going to get a momentary decrease in pressure coming out of the heart, sensed by the aorta. So that momentary decrease in cardiac output, because you just stood, is going to be sensed as a decrease in pressure, stimulates the baroreceptor reflex to constrict blood vessels, primarily in the lower part of the body, to force blood back up towards the heart, to oppose gravity. And so that's going to then, negative feedback mechanism, increase arterial pressure. This mechanism fails in elderly people. They develop what's called orthostatic hypotension. Orthostatic just means change in posture. Hypotension, low blood pressure. So elderly people whose baroreceptor reflexes don't function as well as they used to, stand up too quick, they get dizzy, lightheaded, faint. Some medications can also interfere with this and make you lightheaded, prone to syncope. So the chemoreceptors here are also sensitive to chemicals. So you've got the baroreceptors for pressure, but you also have a chemoreceptor response. Chemoreceptors are located in the same place as the baroreceptors. Carotid sinus of the internal carotid arteries, and then also the aorta. So changes in blood chemistry, low oxygen, high CO2, low pH, right, indicative of exercise, are stimulating the vasomotor center to stimulate sympathetic activity to raise blood pressure, right, increase blood flow. Now these receptors have varying sensitivities. They're primarily sensitive to oxygen, PO2, somewhat sensitive to pH and less sensitive to CO2, but they do sense all three. The other thing is they really don't respond unless arterial pressure has dropped also, because the baroreceptor response is much more noticeable. So if your blood pressure, your mean arterial pressure falls below 80, then the chemoreceptor response can kick in. But when you're above 80, you're in that hypersensitivity zone for the baroreceptor reflex. Right? Optimal is about 100. So in that case, the baroreceptor reflex is going to be more controlling. It's going to be more active. Question? All right. Let's talk local control. So individual tissues can control blood flow based upon need for oxygen, need for nutrients, need to get rid of waste products. And so we're dealing with delivery of oxygen, delivery of nutrients, and removal of harmful metabolites like CO2 and hydrogen ion. So the flow is going to be closely related to the metabolic activity or the metabolic rate of the tissue. Blood flow to the brain is almost always constant. Cardiac output to the brain doesn't change very much. What you can do, though, however, is you can alter blood flow. If some brain areas are more active than others, then they can increase blood flow to themselves. But as far as total cardiac output to the brain, it always stays constant because you have to remain conscious. Right? That's your most important organ. For other organs, you can regulate flow pretty drastically, particularly muscles. Increases in tissue metabolism are going to obviously increase blood flow. The need for more oxygen, the need to get rid of CO2 and hydrogen ion. There are two major theories for this local control, this acute control of blood flow to tissues. The vasodilator theory and the oxygen demand theory. We're going to discuss them both. So let's go back to something I talked about in the Camtasia that I recorded for Monday, Poiseuille's law. Q equals delta P over R. Control of flow through a blood vessel is determined by the pressure gradient in the vessel and the resistance of the vessel. The vasodilator theory for blood flow control says that blood flow control locally is going to be controlled by paracrines, substances that are released locally by the tissue because of this demand for increased blood flow. So increased tissue metabolism increases release of vasodilator substances. causing dilation, which decreases resistance to flow, and thus flow goes up. Substances that we know control blood flow to tissues. Constrictors, epinephrine and norepinephrine stimulating alpha-1 receptors, which we've talked about ad nauseum. If anybody misses that question on the test, I'm going to take off an extra point. I'm just kidding. Serotonin. Serotonin is important in clotting, among other things. So serotonin can constrict vessels, especially during vasospasm. Angiotensin II, arginine vasopressin, which we call ADH, antidiuretic hormone, and endothelin. The vasodilators that we're going to deal with, so epinephrine, norepinephrine, stimulating beta-2 receptors, primarily epinephrine, the binding affinity for norepinephrine and beta-2 is really low. Histamine, causing vasodilation, that's also part of the inflammatory response, increasing swelling in tissues. Bradykinins, prostaglandins, nitric oxide, all potent vasodilators. So the vasodilator theory says that when there is an increase in demand for blood flow, you'll get an increase in release of these paracrine molecules or endocrine molecules in order to adjust blood flow accordingly. Nitric oxide we've talked about before. There's a number of factors that go into release of nitric oxide. It's synthesized by nitric oxide synthase, NOS, from arginine, amino acid. So stretch, inflammation, stimulation by neurotransmitters can cause an increase in activity of this enzyme. So you'll get production of nitric oxide, which is freely diffusible. It's an uncharged small gas molecule. So it freely diffuses across cell membranes. You can, it binds to, stimulates guanylyl cyclase in smooth muscle cells, converting GTP to cyclic GMP in order to relax smooth muscles. This also happens to be similar to the mechanism for Viagra and the other ED drugs. Blocking phosphodiesterase activity means cyclic GMP continues to accumulate in the cells, stimulating relaxation. Tissue oxygen, the effect of tissue oxygen. When you look at, under normal conditions, arterial oxygen saturation, you see down here under normal saturation conditions, there's very little change in blood flow. Bless you. But then as you see a drop, usually around a PO2 of about 60 millimeters of mercury, then the curve shifts from being something of a flat region into being a higher rate of change region. And that's where you're going to see a dramatic increase in blood flow. This effect especially affects muscle cells. Right? During exercise, oxygen demand, the PO2 in those vessels traveling through the muscles is going to drop precipitously as those muscle cells are sucking oxygen out of the blood. And so those vessels are going to dilate in order to increase blood flow to those tissues. Come on. So the oxygen demand theory says that an increase in tissue metabolism or a decrease in oxygen delivery is what is going to stimulate vasodilation. That's going to decrease the arterial resistance. So it's a chemo response rather than a response to a released paracrine or endocrine substance. So metabolic vasodilators that we are aware of, the one that is most potent is CO2. High interstitial fluid CO2 is a potent vasodilator. That means that these cells are highly metabolically active. They're making a lot of CO2 as a byproduct of cellular metabolism. Got to get rid of it. It's a toxic waste product, so blood flow increases. Temperature. Temperature is another thing that's going to dilate blood vessels. To a lesser degree, oxygen and pH. So primarily it's CO2 and temperature, but oxygen does have an effect. And because of the conversion of CO2 to carbonic acid, CO2 and pH tend to go together. Other autoregulation theories, metabolic theory, which is basically oxygen delivery theory. Myogenic theory proposes that as arterial pressure falls, there's an intrinsic property in muscle, causes them to dilate in response. The evidence for that is limited. I'm just presenting it. I don't particularly think this is the primary theory. And then individual tissues, individual organs have their own mechanisms for controlling blood flow, right, that are special to that tissue. But this one means, this metabolic means, is common to all tissues. Questions on local control of blood flow? Long-term regulation. Long-term regulation is going to involve the endocrine system. One of the things you do when you exercise is you stimulate a process called angiogenesis. When tissues have a higher demand for oxygen, they tend to grow more blood vessels. This is one of the ways by which cancer spreads. Cancer stimulates angiogenesis so that it can get an increased blood supply. One of the ways of treating that is to block angiogenesis or deprive the developing tumor of oxygen. So tissues that are highly metabolically active will grow more blood vessels. One, there are a few components to muscle growth associated with exercise. One is increase in actin-myosin filaments, so hypertrophy of the cells. The other is angiogenesis, increasing blood flow, which causes muscles at rest to appear bigger because of their increased blood component. So in angiogenesis, what you're doing is you're stimulating the arteries, the small arterioles, to branch out and grow new arterioles to feed the tissue so that the tissue can get more and more oxygen and nutrients because of its high metabolic activity. This will happen in tissue that's ischemic over a long period of time. So if you have a tissue that's deprived of oxygen over a long period of time, it will try to grow new blood vessels to feed it. Tissues that are rapidly growing, like tumors, or say during puberty, when you get a growth spurt, you're going to get an increase in angiogenesis. Tissues with high metabolic rates. Right, so muscles during exercise, if you use areas of your brain a lot, you'll increase angiogenesis. to that segment of the brain, etc. Most of these angiogenic factors are small growth factors, so they're related to IGF from the liver, insulin-like growth factor, but they're smaller paracrine molecules. They're not endocrine in nature. They're localized to the tissue. So vascular endothelial growth factor, sometimes called VEGF. Fibroblast growth factor, especially important for connective tissue remodeling. Now, other reflexes. Atrial and pulmonary artery reflexes, increases in blood volume, increases in venous return to the heart, will increase atrial stretch. Increasing atrial stretch releases something called atrial natriuretic peptide, ANP. If you want a good way to remember ANP, it does the opposite of aldosterone. Right? Renin is released when blood pressure is low, stimulates production of angiotensin II and aldosterone. Aldosterone causes an increase in sodium reabsorption in the kidneys. ANP is released when blood pressure is high, atrial stretch is high. So if you decide to down, say, half a liter of water in a short period of time, that's going to get absorbed into the system. You're going to have more blood volume. That's going to increase atrial stretch. You'll get release of ANP. So ANP does the opposite of aldosterone. So instead of sodium being reabsorbed, sodium is now not reabsorbed and left in the filtrate. So you're reabsorbing less sodium, which is going to mean more volume can be urinated away. Right, so it's the opposite effect of aldosterone. Also an increase in renal sympathetic activity for atrial stretch in order to increase filtration. So you can get rid of more volume. And also there's going to be a decrease in ADH synthesis as well. ADH is released when osmolarity is high. If osmolarity is not high, I'm not going to release ADH. So overall, the factors that we have that are going to affect vessel radius, things that are going to affect that peripheral resistance or systemic vascular resistance, are all listed here. Right, and I've already gone through them all. You've got nitric oxide, you've got serotonin, epinephrine and norepinephrine. Any questions on anything related to cardiac output and systemic vascular resistance? All right. See you on Monday. All right. Cool. Yep.